Okay, we are live. Alrighty, so hello everyone. Thank you all for joining us this afternoon. Today we have Dr. Yurko, Ron Yurko, here coming to speak about his work he's done as a sports analyst. Um, and yeah, I'll pass it on to him to give himself a, a longer introduction. Yeah.
All right, thank you. Okay, so just to say who I am here, I'm Ron Yurko. I just finished my PhD in the Department of Statistics and Data Science at Carnegie Mellon University. Did my undergrad at CMU back in 2015. I just finished PhD in May, and I'm currently a teaching professor in the Statistics and Data Science Department. Just started officially this fall. Before that, I worked in finance in between undergrad, grad school. I then, while I was an undergrad, I interned for the Pittsburgh Pirates, baseball operations, data and analytics intern. And I realized then I didn't personally want to work for a team full time. Team lifestyle is very committed, working on a lot of day-to-day tasks, and I became interested in research. So that led me to the path of eventually deciding to go back grad school, PhD. While finishing up my PhD, I also did some part-time work with a company called Zealous Analytics that I worked on the side of consulting with NFL teams on research projects with player tracking data, which is I'm going to talk about here today. And I've also then in the time between undergrad and grad school, I publish a lot of research in sports analytics. It's one of the things I love. It's what got me interested into statistics in the first place. I love baseball and loved fantasy football. And so it's what motivated me to where I'm at now. So I want to just kind of talk about a few different types of sort of like what's the modern state of sports analytics type research that's going on. So just a very brief history lesson. Data and sports have been connected since the beginning, essentially. This is old school box score stats, 1870s baseball game. But obviously, technology has changed and improved over time. So we can get a lot more information now than just what used to be recorded hand by hand and put in a newspaper. And so I'm sure people on this call and whatnot, this meeting and class, you've heard of Moneyball. All right, so the book was actually published in 2003, sort of chronicling how the Oakland A's were using analytics in the 90s and 2000s. And then, of course, there was the movie released in 2012. This book, I read this book when I was like in middle school, high school. Not at that time, I'm not that old. I was a little bit later. But it got me really interested in thinking about statistics and sports. But now, at the time, things have sort of changed since even the idea of what was considered in Moneyball, the types of ways of advancing using data and information to improve the processes of different teams. So before, sports analysis kind of used to look like this, where I have this x-axis here corresponding to some period of time. And let's say I have like a starting value on the left-hand side, and then I have an ending value on the right-hand side. And so I'm just going to say I observe some difference in this beginning and ending value. And this could be, a team score before or after a play occurs. Someone at the end of a possession, the score changes, or whatever event a play is run in football. And so or maybe a period of time we're thinking about, there's a change in the score. It's very sort of discrete look of sports. One simple example is looking at in baseball, softball, run expectancy. So on the left-hand side is this little base out figure showing you what looks like the base situation in terms of bases empty, first, second, and so on. And then we can have like the number of outs associated with that. And then the table on the right shows you, okay, what's the expected number of runs to be scored? So this is actually something we did with our Division III softball team at CMU, run expectancy values for D3 softball to help with the coach in terms of thinking about like strategy and whatnot during games. But we have a situation and we could look at, okay, we start with bases empty situation. We have some expected number of runs. And then we have some change in that in terms of going from bases empty to a runner on second base. All right. And so thinking of, okay, I can look at then the difference in that value, say what has happened then in terms of the change in the states from someone hitting a double in this case. There's a change in that run value that I can attribute then to that event taking place. Just looking at 1.29 minus 0.69. Football is a little bit different. It's a little bit more complicated than baseball. And so in this case, I have two examples of our plays in football. Left-hand side, I have someone running in what looks to be a 10-yard gain on like a 3rd and 15, for instance, versus on the right-hand side, I could have a 3-yard gain on maybe a 4th and 1, 4th and 2. The shorter carry on the right-hand side is worth a lot more than the meaningless carry on the left-hand side where then the team follows up and punts. There's a lot more context that goes into just even thinking about what's the value of a situation in football. So football data, the classical sense is working with what's called a play-by-play data set. Each row is a single play. We know who's the team with the ball. We know the context of what's the down. So 4 downs to advance the ball to get a first down or score. You either get a new set of downs or you're turning it over on defense. You have the yards to go for a situation. The how many yards to advance for the first down, or if you're at the goal line, where the yard line the team currently is at, how many yards from the opponent's end zone, and then also context like the time remaining. All right, so knowing, okay, just how many seconds are remaining in the game. So what we really have also that we're working with are series of plays in these drives. And what we're interested in a situation is just what's the value of it from a points perspective. And so what I could think of is the next score to take place, given where the team is at with the ball at a current situation. What's the next scoring event that will take place in the half? And no score could take place. 0 points, both sides. The team with the ball, they could go down and get a field goal. They could go down and get a touchdown. Maybe they get a safety on the opponent if they march all the way down the field, turn it over. Or the opposing team can do the same events. All right, so we have for the team with the ball scoring these points against the opposing team could score those points, or we have no score going on at all. So the way to do that in terms of modeling these different events in this context for predicting then the next scoring event in American football, use a multinomial logistic regression model. All right, so I'm not going to go too much into math today, but some of the things just to show you. All right, so this is log odds equations with the different events that we have. And for multinomial models, instead of just simple binary outcomes for logistic regression predicting yes, no, I have k categorical levels of a variable. All right, in this case, I have all the different scoring events. And what we need is a reference level. This ensures us that we can make a valid probability. So these things are going to sum up to 1 at the end of the day. And the reference in this case is a no score. And so we have a separate equation then, effectively for each of the different events, the scoring events that could take place. Probability of a team scoring a touchdown relative to nothing happening. Probability of a field goal taking place relative to nothing happening. And this can be converted then into expected points by just simply taking the sum of that value, 7 that we're putting in for a touchdown, 3 for a field goal, and multiplying it by the predicted probability of that event, given the information I have about what's going on in terms of that context that I have. So just in terms of giving you a sense of what this looks like at the end, this is showing you the x-axis here are the yards from the opponent's end zone, starting from 0 on the left-hand side, meaning right up against the end zone, about to score a touchdown, going 100 yards away, pinned up at the back of your own end zone. And then the y-axis is the predicted probability of each of these events that are denoted with the different colors. Darker blue being good for the team on offense, darker red being good for the team on defense. And then it's faceted here by the different downs, 1st to 4th down. And so the obvious thing that jumps out when you look at this dark blue line is really high up for teams right up against the end zone. They're about to score, much more likely to then score a touchdown. All right. And we see differences in behavior as you go across downs. This line here is the field goal probability line. So on 4th down, the probability of a field goal is just going much higher. All right. And that's due to team behavior. So this was based on data. Technically, this paper was published in 2019, even though the paper was done in like 2017. That's the slowness of academia. So the data was like 2009 to 2017. So things have changed since then. These types of curves that people come up with now, if anyone in this club is familiar with NFL FastStar, they used our methodology, and they just use a different approach for fitting the model. It's the exact same thing. And so it changed then. These curves will look slightly different based on how teams have sort of updated behavior over time. They're not kicking as many field goals, they're going for it more and whatnot. But this is giving you a sense of just what these probabilities look like. It's not a simple function, easy basic thing. And this is just aggregating this information to be on the x-axis, yards from the opponent's end zone, y-axis being the expected points value. So I'm basically taking those probabilities on the previous slide, multiplying it by the point value, summing them up to get one number. And so this is showing you how it compares as we go across the downs, effectively like parallel lines with some smoothness going on. And the 4th down, the expected points is lower than the others because of that field goal probability. So this is a high level explanation of sort of what we need to do for football. That's a lot more complicated than what goes in to get like a point value compared to something like baseball or softball. If we're interested in is how do we actually evaluate players, all right, in American football, in the NFL, in college football. And so as I said before, we can look at something very naive, just what's the expected points at the beginning of the play? What's the expected points at the end of the play? And I have this expected points added, this change in value. It could be positive, it could be negative. But what I care about is I want to divide the credit of that change amongst all the players on the field. And I need to do that somehow. That's a really difficult problem. And so one of the ways, the classical way of doing this that started in basketball, introduced by Rosenbaum back in 2004, was to use some form of adjusted plus minus. So plus minus is a very traditional sports stat you see in basketball, hockey, just what's the change in score differential when a player is on the court versus off the court, and just attributing that to then their performance. That's naive because maybe a player is always going up against the best opponents, their team stinks. There's things you want to try to handle. And so what people do is they can do a simple regression approach for this, where yi here, the response variable, is some change in value for some period of time. And then I have indicator variables, all right, a bunch of variables now, just reflecting if a player is on offense, if they're on the field on offense, or maybe another set of indicators for if the player is on the field for defense. And maybe I adjust for things like home field advantage. But what these types of approaches do is you have a giant matrix that is a collections of ones, zeros, or maybe one, -1, to do these different ways of denoting if they're on offense versus defense, home versus away. For every player in the league, it's a giant matrix. And so what that means is you could have then different periods of time where players are on the field and they're going up against different opponents, right? So it's going to be a massive data set, and you're trying to just get a coefficient for a single player. You're fitting a basic regression model and get a coefficient for a player to say what's the average effect for when they're on offense, when they're on the field, when they're on the rink, whatever it is. All right, so this is a high dimensional problem. It's actually really annoyingly difficult because you also have to deal with the fact that in many sports, players are on the field together all the time. So if you learn in your basic linear regression class, I don't know the range of classes people have taken already, but a big problem for simple basic regression is collinearity. And so if I have two players that are on the same team and they're always on the field together, those two columns in your data set are going to be perfectly equal. So how can you possibly tease apart the differences between those players if they're always on the field together? or even if they're not always on the field together, they might differ only a little bit. So their columns will be highly correlated, which is problematic for regression purpose. So one of the ways that people have dealt with this collinearity problem is to use something like ridge regression. So this is regularized regression. We're introducing a penalty term. So you see this in your later stats classes, hopefully, of doing what we're adding here is some bias into our model, where we have our traditional ordinary least squares problem here, y minus x beta, just minimizing residual sum of squares. But now I'm saying I have this lambda times a summation of my squared betas. It's an additional penalty where if the larger my betas are, the larger my coefficients are, my loss function is going to be bigger. So I want that to be smaller. So what I'm adding in here is this additional penalty is to say, hey, make the coefficients a little smaller than what they would be if I just did regular ordinary least squares, if I just did LM in R. I want to have a little bit more shrinkage. And the cool thing when you do this actually, for this problem of collinearity that we have between players, is their coefficients will be equal to each other. If two players are on the field together the exact same time every moment throughout a season, and we fit this regularized regression approach with ridge regression, they will have the exact same coefficients. They will have equal weighting. So that's sort of advantageous then for us to use. All right, so something that's other ways of sort of going beyond this is dealing with Bayesian regression. All right, having priors to try to handle then these issues. All right, so this was an approach for handling soccer data. So this figure on the bottom right here is showing you sort of the differences between major sports. And so soccer, so x-axis is the number of substitutions per game, and then the y-axis is the scoring per game. All right, so the x-axis we can see on the left-hand side here, soccer, very few substitutions per game. So when players are on the field together in soccer, all right, they're on the pitch together, it's very rarely that it's changing. All right, they're primarily always on the field at the same time. We see very few differences for a team if someone's playing with a different set of people. Hockey, there's constant shifting, constant changing. So we constantly observe potentially differences with players and who they're going up against. One of the issues, though, is the fact that they will move in a line together. So it's the same line going with each other. But one of the other concerns is dealing with the fact of how many events do you have? This is a level of scoring that takes place. And so soccer is low scoring, low substitutions. It's the most difficult sport to model in this sense. Basketball, high amount of scoring, many events taking place. And you have decent number of substitutions that you can do a pretty good job then of inferring like the ability of a player. So you see ESPN has like a real plus minus standing of player rankings. It's based on this approach. All they're doing is this type of regression, accounting for some ridge regression penalty and whatnot to get a better sense of how good a player is while handling who they're going up against, who's on their team. Soccer's the most difficult because of limited substitution, limited events. So we had a group of students at CMU, PhD students, not undergrads, who did this idea of let's use FIFA ratings as a prior. And so what we see here is we're saying the coefficients for players are effectively going to be shrunk towards the FIFA rating that they were given at the beginning of the year. And what that means is once you start to observe more data, you move away from those FIFA ratings. And so players that might have been on the field together all the time, they're effectively going to be separated by the FIFA ratings that they had at the beginning of the year. That prior is going to tell us who's actually maybe a little bit better than the other player. This, though, is a stupid idea at the end of the day, really oversimplification of sports. Say, hey, there's a beginning and there's an ending, and it's ignoring everything that happens in between. Sports in reality actually looks something like this, where that value's changing in continuous time. You know, it could be going up and down. You have a play taking place. Players, all other sports are very different from baseball and softball, which I love baseball, but at the same point in time, it is boring compared to everything else, right? Someone stands, they hit, they stop. They take too long to then throw another pitch, and so on. All right, it's very discrete. All other sports, there's a lot of continuous movement happening. And so the value that's changed, it's constantly changing up and down throughout plays. So tracking data has enabled us to figure out and try to understand more how to actually figure out this type of continuous time value. So what's being displayed here is just an example possession from a basketball game a number of years ago using tracking data. You have one team represented by blue dots, another team represented by gray dots, and then we have a little red corresponding to the ball moving around. Eventually, players moving, tries to take a shot and whatnot. All right, so there's a lot of data here. X, Y coordinates for every moment in time throughout the plays. And then you have this for all these games, different seasons and whatnot. And so what people did a long time ago now, back in 2016, Dan Trevone, he was Harvard PhD in statistics, worked for the Los Angeles Dodgers for a number of years, left right before they won the World Series, even though he claims the Astros robbed him of one. He now works for Zealous Analytics. And he introduced this seminal approach of trying to model this type of stock ticker on the right-hand side. What's the expected value of a current moment of time where the player has the ball? And you can think of what goes into that, the different types of predicting the probability of a pass taking place to somebody, given where the player is currently at. What's like the shot value, all right? Do they decide to take a shot? If they decide to take the shot, what's the probability of the shot going in, given the spatial information that we have, all right? There's a lot of models that go into this, predicting the movement of players, all right? Predicting where will they go forward and whatnot. So we can see how this stock ticker changes over the course of the play. You can see how there's increase in movement here as the player gets closer and closer to the hoop, right? The expected value goes way up at that moment in time. So how do we do this though for football? And the great thing for football in recent years is there's been the big data bowl. So the NFL has tracking data where they have chips in the shoulder pads. So these RFID chips use like this infrared camera technology. It's like a gold standard actually for how to get tracking data. But we get information about players and the ball on the field every 10th of a second. So we know where players are at every 10th of a second for every play and every game now. And what we can do with this information, we know how fast they're moving. We know actually now the orientation of the player. So what I mean by that is which way their shoulders are facing. We also know like the direction they're moving in. And now we actually know what's their intended sort of direction they're facing. And so it's very rich data that we can work with. And every year there's been this big data bowl that's releasing new samples of the data. And so what we did was a group of us at CMU, PhD students at the time, everybody else that I worked with now works at Google, and I'm the only one that remained. What we did was worked with a sample of this data from 2017, first 6 weeks of the 2017 season. This included everybody on the field. So different big data bowls in recent years have had different themes, and they've restricted sort of like, because the teams are interested in hopefully seeing people work on projects in this, they don't want all of the answers to be in the public. So data sets that get released might be certain types of players are removed. A couple of years ago, the big data bowl was on passing plays. All linemen were removed from the data, all right? The initial version had everybody. First 6 weeks, 2017, with everybody on the field. So it was really rich data to work with. Obviously, it wasn't a full year, but it was still a lot of data to handle and work with. So what it actually looks like, you have for every player, for every moment of time. So a moment of time is represented by the frame ID here. It's like a timestamp, all right, just a unique moment of time within a play. You have then the XY position on some space, on some grid on the field where a player is at, you know, the speed, the direction they're moving. The NFL also includes these event annotations telling you like, hey, this is where the handoff took place. This is when the snap took place. This is when the person was tackled, first contact, scored a touchdown, made the catch, etc. And you have this for every single player and the ball. All right, it's a lot of information. So when we show you an example play, this was back in 2017, oddly, Cordell Patterson. So for anybody that plays fantasy football, he's a running back now, but back in the day, he was a wide receiver where he did a jet sweep touchdown run. And so he was on the Raiders. He's on the blue dots of the Raiders. He becomes a black dot once he receives the ball, and he's running down side here. The orange are on defense. They try to get him. They can't. All right. So he scores a touchdown over the course of this play. It's 47-yard jet sweep touchdown run. And so what we might be interested in then is thinking about how does the value of this play change over time? And so we have the moment of snap. Players are on the fields arranged in some way. And then we have on the top right here, we now have the handoff. Players have moved between snap to handoff. How has the value then of the situation changed? What's the expected yards that running back, wide receiver in this case, that he will get by the end of his run? And then we also have like the moment of first contact. What value does Cordell Patterson provide after he's actually contact has been made with the defense before eventually ultimately arriving at a touchdown? When's the moment that we're going to observe that it's very likely that Cordell Patterson's going to score the touchdown during this run? So we want to figure out, like, how do we use all this information to try to model this sort of process that could be useful for sort of breaking apart who's adding what over the course of the play? What effect does the offensive line have here? What effect does Cordell Patterson have here? And so a long sort of process that's in general, it took months of discussing and working on to try to break down what would be the flow chart for every single possible play in an NFL game. And I'm not going to go through all of this. At the end of the day, everything comes back to once someone has the ball, where are they going to end up at? And so what I'm just going to focus on here is if someone has the ball, we're focused on running plays. Predict the ending yard line, how far they're going to get at the end of the play. All right. There's all sorts of process you can have in terms of if the QB throws, who are they going to throw it to? Is it complete? Is it not complete? Is it going to be an interception? There's all these different models that can go into modeling every single play in a game. And so some of the work I did with Zealous in my final year of grad school was on building sorts of all of these different models to arrive at a stock ticker for football games. Now, I'm just going to talk to you about this one here at the bottom, this ball carrier model, and thinking about what's necessary for this. And so one of the things for tracking data, that table I showed you, X, Y, speed, directions, it's a lot of information, but it's meaningless in its raw form. And so if you're someone that's interested in working with sports data, sport and player tracking data specifically, if you're looking to do the big data bowl, most of your time is going to be spent on creating interesting variables, feature engineering, right? Creating things that can be informative. For instance, the distance between the person with the ball and the defender, where are they at in terms of the target end zone versus the sideline? What's the angle difference between the direction they're moving and the defender's moving? Computing these various types of distance quantities could be informative for doing something to predict, all right, where is the person with the ball going to end up at the end of the play? All right. The raw data doesn't have this for you. You have to do a lot of data manipulation and wrangling to construct these types of features. There's also things called Voronoi tessellations, where you try to partition the field such that a player owns a space. All right. And so these are two arrangements showing you these types of tessellations where each player has a region, these different types of polygons, and we could think about constructing useful predictor features based on these polygons. All right, based on these Voronoi tessellations. When a player owns a space here on the right-hand side, that includes the end zone. All right, they are the closest to that strip that goes into the end zone than anybody else on the field. All right, and so maybe that itself is predictive when they have a space that they are going to be likely to get and score a touchdown in. All right, so what we could do, building a model. So this is based on a deep learning model, actually, taking a lot of information, and this red line is showing you what's the predicted end of yard line for a running play here. All right, so we can see how this line is changing over the course of the play. All right, trying to predict, given a bunch of high dimensional features, where Cordell Patterson will end up. So we can see at the very beginning, it actually looks like it's going to be a long run just to start with. And then we can see how it's gradually changing the more and more he goes downfield to eventually to the point where it's, yeah, he's going to score a touchdown. And so just to give you a sense of like the type of information that's relevant here, we can see the distance and closest defender, how's that changes. So drops down near 0 at the point of first contact. So tracking data is not going to be perfect. All right, it's based on chips and shoulder pads. So even though the NFL told us someone made contact, they're not actually being touched based on the tracking data. But you can see how then separation goes back up and down, and then goes up again right before they score a touchdown. One of the key things here on the bottom right is just the ball carrier speed. Cordell Patterson was maintaining a high level of speed all the way throughout this run, right? A lot of basic running plays don't see this type of behavior. This is something that's kind of unique that these sort of jet sweep runs. And so then we can see that those questions I was wondering about at the beginning, how does it change at the different moments of time? So we can see at handoff, this was predicted to be a pretty big run just at the beginning. And at the moment of first contact, had a good prediction on where they were going to go. And there's even this moment right after first contact where it was a signal of, hey, Cordell Patterson's actually expected to score a touchdown here under this approach. It's not surprising given this sort of gap or the lane you can kind of see that's visible down at the bottom. Now, this is great and all. We can see on this bottom here, just this change in terms of the yards from target end zone at the end of the play. And what I'm interested in, though, is a stock ticker. All right, I want to get a continuous time value for a football play. So I'm going to take then my predicted end of yard line, and I'm going to go back to that slide at the beginning that you might not have paid attention to with all of the multinomial logistic regression equations to say, I'm going to update the X's there. I'm going to use my predicted end of yard line to change my down, my yards to go. What'll be my predicted new situation to then get new probabilities for the different scoring events. So these will be predictions of what will be probability of touchdown, field goal, and so on at the end of the play, predicting the expected points. And this could be plugged in expected points models, win probability models. And so the whole thing here that I'm showing you is while this play is taking place, I have the red line changing, and then I have this expected points, the stock ticker now. If I plug this in to see at the beginning of the play, Raiders expected points to this current start was like about 3. And then it's gradually increasing over time until we eventually get to the point where it scores a touchdown. And this touchdown actually gave them the lead in the game. So their win probability was below 0.5. And then as the play took place, and eventually we got to the point, hey, they're expected to score, it crossed the 50 probability mark. All right. It was actually, hey, they took the lead. They're more likely to win the game now. But the annoying thing here is this is not actually a valid approach for coming up with this stock ticker symbol. All right. This is not an expectation of expected points or win probability. What I just did was I took a fancy machine learning model to get a predicted value of this really complex utility function. And there's this great theorem of statistics, the law of the unconscious statistician, that in order to get an expectation of a complex type of function, I need to actually integrate over the range of values for that complex function. All right, I'm not going to go into all the details of the math here, but what I did was just invalid. All I did was plug in one single value and say, hey, use that, plug in that predicted yard line to then get what the expected point should be. What I really need is a probability distribution over the yard lines. All of the likely destinations a ball carrier could end up at. So what this figure is now showing you is every single yard line on the field here now has a red line. The darker the red line is, the more likely it is the ball carrier will end up at that spot on the field. And what you can see on this play is there's this line over near the end zone that starts to get darker and darker throughout the course of the play. And so this is actually a sort of bimodal distribution showing you that there's this probability of Cordell Patterson being tackled near where they currently have the ball. But then there's this probability of Cordell Patterson going all the way to the end zone that gets increasingly more likely as the play goes on. So the mean, that red line I showed you in the previous slides, the mean is somewhere in between those things, all right? And the mean is a flawed measure when we care about probabilities. The mean is just an expected value. You learn about the mean, the challenges with using a mean for a skewed distribution in an intro stats class, all right, and how it's affected by the tail. Same thing applies with distributions here that are not symmetric. All right, you're modeling the yards gained by a player. It's not going to be a symmetric looking distribution. All right, it's going to have to be something with a tail that's capped. So what we do is we take advantage of approaches that are actually used for modeling hurricanes, using random forest for conditional density estimation to then model football player movement. And so then we can predict the probability essentially of a player ending up at every line on the field. All right, I'm not actually predicting it in a 2D space. I only actually need along one dimension. I just need the 1 yard line. And with that, I can then, so just to give you a snapshot, like at this moment of time here, this curve is representing the dark red lines observed. So it's very likely at this moment in time at the first contact that Cordell Patterson was going to get tackled near where he was at. But it was also kind of likely that Cordell Patterson was going to get a touchdown, relatively speaking. Like there was a non-zero chance that that could take place. But using this, and so another example here, this was actually I think this was a 97-yard run. As this takes place along the x-axis here, giving you a display of like that probability that they're going to end up at this moment on the field. So there was always this like non-zero chance that they're going to get tackled where they were at, but eventually this end zone line keeps getting bigger and bigger over the course of the play. So using this then, I can actually get a smoother line for my stock ticker to say, dealing with the probabilities of all the different types of outcomes that could take place. I don't have as much of a jagged line now. The left crossed out on the X was what I used to have when I was just plugging in a single point prediction. And now with on the right-hand side, I have all the probabilities of the play ending at different lines on the field. And so this stock ticker is a little bit more smoother. It's not as jagged. So you can still see then how the expectation of my complex utility functions, expected points and win probability, changes over the course of the play. And so the issue still is, how do we use this to figure out how good all the players are on the field? This is great and all. It's a complicated process I just walked through. I still don't understand who deserves credit for what. I still want to figure out that process. And so this is still ongoing active work by everybody in sports. People in teams, people in public research, people in media, trying to figure out how do we use tracking data to accredit players. And so one idea is evaluating the performance relative to ghosts. So this is a single snapshot of a passing play where I'm going to say, all right, the player, the defender marked in red, we observe, given where they were at in red, this is the predicted probability of where the person that just caught the ball will end up on the field, this red line. And so it's very likely that that receiver was not going to get a first down, represented by the gold line. But I could predict where that defender would be on average, given all the information I have over the season and given where all the other players are at arranged on the field. So on average, we actually observed the defender to be this sort of charcoal dot here. So if the defender was not at red, but moved to this black grayish dot here, the distribution shifts. And it's much more likely that the receiver would get a first down. And so we can think of ways of trying to say, hey, by the placement of this player, this player shifted then the probability of a receiver getting a first down for whatever reason. Maybe that was by the play call design, or maybe that was just the defender's intuition and how they decided to cover that receiver. They pressed up more against them, and they limited then that receiver's ability to get a first down, right? Versus what we expect the average defender to do. And then we get constructing then various types of new statistics based on how players do relative to what we call these ghost players. The ghost being that black dot there, what we expect a player to do in a situation. All right, and so seeing how maybe certain players are better than expected under these sort of ghosts. And so this was back, I think, in 2018, the data for this. So at the time, the Chicago Bears defense was really good. Obviously, they suck now, but. So the thing just in this is still really ongoing research. All right. Working with player tracking data. So NFL Big Data Bowl, as I said, is a yearly competition. This was the winning submission last year by Robin Ritchie and others at Simon Fraser University. This is trying to model what is the optimal path for a punt returner. And so this animation here shows you this gray line of what was the actual path the punt returner took. And then the black being what was the predicted optimal path. Given all of these distances, these lines you see connecting each of the players, these windows, knowing how each of those players are moving, their velocity vectors, where they're at positionally, to say figure out, okay, what's the expected arrival time of this defender to this spot on the field, given how they're moving. All right. And then figuring out from that process, what is the best way for this punt returner to take the football. All right. So this was the winning submission. People on this team are already working in different sports. One's in baseball, one's in hockey. Robin's still finishing her PhD, and then she's going to get hired by someone somewhere. But this is effectively the biggest outlet right now, if you're interested in sports analytics, to showcase your skills and potentially get a job. The Big Data Bowl every year. You don't have to be interested in football. People that do this, they get hired by baseball teams, basketball teams, hockey, etc. It does not matter. If you're interested in wanting to work in sports, this is a must-do event. So this takes place every year. It's the way to showcase. You don't even have to win to get hired. All right, people post their submissions on Kaggle, and you can see the type of work that people have done, and you'll be able to share it in your data science portfolio. And so really, and just want to end with some points here about breaking into sports analytics. The biggest thing I'd say is to share your work you do. All right, self-promotion is weird, but it's really important, especially in sports. So 2 students I advised previously, Sarah Malapalli, she wrote a package to scrape next-gen stats images of passing charts. She got hired by the Baltimore Ravens 6 months later. So she gave a talk on how to hack the NFL and get a job really quickly. Then Rishav Duda, he's been with the Cleveland Browns, even though they're a terrible organization, for a little bit now. He figured out different ways of using tracking data and imputing a z-axis, the third dimension, all right, for passing. All right, it's based on like high school physics equations that I don't understand, but it works great. And so now he's been with the Browns since that. And so the biggest thing is sharing your work you do, posting on Twitter, LinkedIn, whatever you want to use. And make sure this year, check out the Big Data Bowl. It's not out yet. All right, the theme's going to come out, I think, this week or next week. If you're really interested in sports, that is a must thing to do. And then we have our own conference at CMU coming up, October 8th, 28th, 29th, 1 month from now. I believe Haley's going to present some way. All right, I don't know if she's going in person, I can't remember now, or doing it virtually. You'll be able to present, you'll be able to attend the conference virtually as students for free. So if you don't want to make the travel out to Pittsburgh, you can just register for free to watch over Zoom. It will be sort of hybrid that way. We're going to have a big in-person event, but still allow people to watch all the speakers virtually. You just won't be able to do, networking and drinks afterwards and whatnot. But definitely check that out. Follow the link there, and let me know if you have any questions about that. So with that, let me know if you have any questions. Just wanted to conclude on there. happy to answer anything in terms of what I talked about, or just general grad school, working in sports analytics, and so on.
Yeah, thank you, Dr. Yurko. That was a very interesting presentation. But yeah, anyone on Zoom or in person, if y'all have any questions, feel free to unmute yourself, drop them in the chat.
Yeah, hi. I thought it was really interesting that you used like hurricane data to model like the positions of your players. So I was wondering like what other kinds of fields you see your work in sports analytics informing.
Well,
you
yeah,
know,
yeah.
s-
So
yeah,
the
go ahead.
technique we used is something that's very common for modeling like hurricanes. Actually, we didn't use hurricane data. The technique though is common in that. And I'd say actually my PhD thesis was actually problems in genetics, and genetics has very similar problems that we see in sports in terms of trying to observe the effect of something, given the fact that it's highly correlated with another variant in your genome. All right. So there's a lot of overlap. When you work in statistics, data science, and whatnot, you see the same techniques and methods that are effectively portable, a lot of different problems. It's the same problems that arise and same types of solutions that you need to sort of work with. So like in this case, hurricane and different story, it's spatial temporal data. It's modeling movements over time. And so with sports now, with player tracking data, you're doing the same thing. So people in other areas have been already kind of tackling these problems in a much more meaningful way. And so we could try to use those same types of ideas for just figuring out who are the best players in sports. But yeah, great question.
Thank you.
Any other questions? Feel free to put them in the chat.
Yeah, we have a question in person. I'll just repeat what Madu said. But she's asking if so does like this sort of research affect like how much a player gets paid essentially?
I will say that the teams that do this, at the end of the day, the goal is to convert all these types of things I was talking about into a dollar value. All right, to say how much a player is worth to the team. And I mean, for instance, the Dodgers have all these sorts of ways of constructing those values, and then they still have limitless amount of money that they can actually spend on players anyway. But it still is, at the end of the day, like how we think about how much a player is worth is the goal effectively for doing this process, right? To hopefully make better decision making then. If we have good valuation for what someone is doing, and then we place a dollar amount on that. And that's a really difficult process itself, because that involves figuring out, okay, how much is a player worth in terms of wins? So that's why it's really nice to do something like on a point scale, because we can kind of figure out from that, we can convert points to wins, like how many points are equivalent to one win. And then from there, how much is a win worth in terms of dollars for the team? So, those are all additional complications, but these are the exact same types of things that teams are doing in order to figure out, okay, should we sign a player or whatnot? A theme in football recently, if you follow the NFL, running backs don't get big contracts really anymore. That's been sort of dwindling down, and it's because it was in recent years, it's a realization that running the ball isn't as valuable as passing, and so people don't pay running backs as much under this expectation that actually it's not as important as other avenues of the game where you should put your dollars and invest your salary cap wisely. Good question.
Awesome. A question I have is, with like this type of research that you've done or seen, does how a player or a team, how they performed the previous game, previous first game, previous two games before. Does that, you take that account to like this type of model, or is that much difficult, or what does that look like?
Yeah, no, that's a good question because in a lot of ways, how this is kind of done is very retrospectively. All right, to like, let's look at a whole season's worth of performance and then figure out how much were they worth during that season. Something that's sort of like mid-season and very like forward-looking, that's a very difficult problem. All right, and so that FIFA ratings one I kind of talked about, that approach kind of went into that because it was the idea of how well can we predict the team's performance given what we've learned about the players so far. And so you can imagine, at the beginning of the year, you've observed a lot less information. So you're not going to be as good. But hopefully if you have some prior knowledge going in, you can be better than just starting off in the most basic way. But there's been work on trying to use, so if you've follow 538 at all, they use ELO ratings for assessing sort of teams' performances based on head-to-head matchups over the course of a season to say like, hey, this team's stronger than other teams, seeing how they go head-to-head. You can do the same thing with players. And with these types of tracking data, you can look at head-to-head contests in terms of when a player wins a matchup and say covering a receiver. And if they had their individual win against a really good receiver, we're going to really bump up their rating even higher. So that type of work is also sort of ongoing and sort of adapting what we know about like team level assessment to players at play level, is sort of trying to appeal to that process to get a better sense of like updating, just knowing what they just did against the strength or weakness of the opponent they just played against, to hopefully be a little bit more informative. Yeah.
Thank you.
Yep.
I have other questions, but I want to open it up first if anyone else has any other questions. Yeah, we have a question from here in person. They're asking if, what sort of softwares did y'all use for these analysis?
Yeah, good question. I personally use R for mostly everything. Some Python for some of the deep learning models that we do, but mostly R for everything else.
Anyone else? I do have another question. So like with these analysis, these research, you're essentially trying to predict the expected value of scoring or how far advanced you're advancing with the ball. So could like this type of analysis be done like live, like during an actual game? Because you're essentially during the game you want to have the highest probability of advancing. So does that kind of happen like in the background?
So it's a good question because the one thing that exists are restrictions that on what teams are allowed to use during games. So a team is not allowed to use a computer to effectively like help with decision making. All right, so the Baltimore Ravens have I think he was a student at Yale, David Stern, I think that might be his name, something like that, where he sits up in the booth and he effectively has like paper printed out with win probabilities of different situations. And so then he could look at on this fourth down and the change, he can then relate, he's connected to Harbaugh over the headset to tell them, hey, we should go for it, we shouldn't go for it. But you can't do it live. All right, can't like sit there and like, all right, my model, toss this in, or I'm gonna see how the play, this value is changing, and like, man, they're really doing something that we should call this play. We can't do that live. You have to sort of you can have like reports ready, summaries, these retrospective looks of something. And the same thing's like for baseball, because like the Houston Astros cheated and we're doing things live, figuring out who was throwing what, for pitches. But you can have iPads set up with information for Aaron Judge to look at what's the tendency of the pitcher and what they're doing, so it can be more likely to hopefully hit a home run, right? You can have static information. You can't have dynamic information though. And I don't know if that's ever going to change.
Okay, awesome. I did not know that.
Cool. Any other questions?
If not, I have one final question.
Okay, cool.
So, do you know about any research that's been done with like observing how big the crowd is to how a particular person performs or a team performs based on the crowd size and like the noise that the crowd's making?
So I haven't seen anything like specifically on that. There's been work though recently on just like the impact of home crowds on games because of with COVID. We had especially in soccer, all these different European leagues where there were no fans allowed at all, right? And so people have looked at, okay, can we get a better sense now what actually the impact of crowds were on the outcome of those games, and see that, yeah, I mean, in certain places it did seem to actually have an impact. I could say like in the NFL there was like home field advantage sort of disappeared in the COVID season. And I mean, I don't know the way if someone's looked at, for instance, like Aaron Judge, all right, it's like constant sort of everyone's watching everything he does, holds up the phone for every at bat right now. If there's anything, to say there's evidence of that's good or bad or whatnot, part of it's because something like that is so extreme that you probably don't have enough data really to make a claim, right? You're only selecting for the best player at that time anyway. But yeah, the home field advantage with COVID's sort of been the only work I think of that has a relation to that.
Awesome. Well, yeah, is there any other questions? Let me stop